Welcome to another video of PIC12F675 PIC microcontroller, and today we will be dealing with EEPROM or E2PROM. EEPROM is electrically erasable programmable read-only memory used to store data. It is used to store read and write data and the data is retained even during power is off. So this EEPROM memory can be very well utilized to store like sensor data or a simple data logging system you can develop with using the EEPROM. So PIC12F675 can provide a let's see how much EEPROM this can provide. So let's get on to the top, and then here you can see that PIC12F675, the device which we will be using today, have only 128 bytes of EEPROM. Has only 128 bytes of EEPROM. So now let's jump onto the data EEPROM in the datasheet. And so in the data EEPROM you can see that we have to use these registers EECON1. EECON2 is not actually used in PIC12F675. It is not for a purpose now. We will only use the EECON1 and the EE data and the EEADR. EE data for the data and the EEADR for the address. And you can very well find the explanation for the registers. E2 data holds the 8-bit data for the read write, and the EEADR holds the address for the EEPROM location being accessed. And they have 128 bytes of EEPROM with an address range of 0 to 7F in hexadecimal. And here is the general information about the EEPROM. You can read it here. And the first register, the EE data register, it is actually a printing mistake. It will be EEDATA, EE data. This spelling is the correct one, and whenever you will use MPLAB, you will have to write EEDATA, this spelling actually. Anyway, this is the data register. It is an 8-bit register. It can hold up to 8-bit data, means from decimal 0 to 255. So 8-bit data, simple, and all these are read and writable. And they can be byte accessed too, since the XC compiler can provide bit manipulation. So you can access bit by bit. And now the EEADR, EEPROM address register. Now since here you have only 128 bytes of EEPROM, so therefore you can only use 7 bits. So bit 0 to bit 6, so 7 bits. The 8th bit is remain unimplemented, should be set to 0. This specifies one of the 128 bytes of EEPROM for read write operation. Now the EECON1 now the EECON2 is not a physical register, and EECON2 is actually not used in the PIC12F675. EECON2 is actually used in higher devices like 16F877A and higher devices. In our microcontroller we will only use EECON1, that is the control register. Con stands for the control, so EECON1 we will use here. This is extremely simple register. Here at the RD, the read initiates when it is written to 1. Initiation EEPROM read, it takes only 1 cycle, and read is cleared in the hardware. RD bit can only be set, not cleared in the software. This is very important. RD bit can only be set. We can only write as RD equal to 1, but we cannot write RD equal to 0. In the software we cannot write RD equal to 0. When we write RD equal to 1, the read initiates, the read cycle initiates, and after reading is complete, the hardware inside the microcontroller automatically turns it to 0. It automatically turns the bit to 0. Now the write control bit, it is also similar to read. When set to 1, then it will initiate a write cycle. This bit is cleared by the hardware once the write is complete. The write bit can only be set, not cleared in the software. So we cannot write as WR equal to 0. The software will automatically clear the write bit after the writing of the data is complete. So we can write as WR equal to 1. We have set the write bit, so we set the writing operation, and so then now we can use a while loop, like while WR. So while WR is 1, then we wait there, and after the writing is complete, then you can do the next tasks. So we can use like that, but you cannot write as WR equal to 0 in the software. The hardware automatically clear the bit after the writing is complete, and we can utilize this like if we can use while, like while WR and then wait. And now the WREN, it will have to be set to allow writing operation. Nothing complicated, just set it so that we can write data. And WRERR, it is an EEPROM error flag bit. A write operation is prematurely terminated by any MCLR bar reset or watchdog reset during normal operation or BOD detect, and if 0, the write operation is completed. And this is an error flag bit. We need not to use it right now. We only will deal with these three things, and the rest are unimplemented and 0. And you can see here many other informations about the reading the EEPROM data memory, writing the EEPROM data memory using assembly language codes. You can see here, and there are various instructions, protection against spurious writes. You can read it from here. This can be home task. You open the datasheet and read everything that is written here. They contain various vital informations. And now we will use the MPLAB, and we will not use assembly language, we will use C code. Now in the code in MPLAB, firstly the pragma configuration bits with the internal clock set, and the main thing here, we have used the EEPROM underscore routines.h. It actually comes along with the X8 compiler when you will install the MPLAB IDE. So if we hold control over this and click, you will open up the EEPROM routines.h. So here at the bottom you can see that here are two functions, EEPROM underscore write and EEPROM underscore read, and obviously the EEPROM underscore write will have void, and here you have two parameters, the address and the value, and the EEPROM read will return unsigned character, and it has only the parameter of address. So we will use them. So we will just write here a random data like 0xAA, a hex data as 0xAA 8-bit data into the first 0th address, means 0x00 or equivalent to 0. So we will write 0xAA to the first position, means the 0th position, and then we will verify that whether the writing is correct or not. So if EEPROM underscore read at the 0th address is equal to 0xAA, so the onboard LED will light up. So if the after writing, if we verify that if the writing is correct or not. So if after reading, if the data is the same as that you have written, so then we can verify that and then turn the GPIO 0 to in which we have an LED connected to we will light it up, or otherwise if it is incorrect, then the LED will not light up. So this is just a simple code. You can find the code from the GitHub link given in the description. So we will upload the code and see whether the LED is lighting up or not. As per the code we have written, the LED should light up, since we are comparing with the same value here. So the LED should light up here. Let's see. So we will now build this project here. So build successful, and now we will upload this sketch. The LED should lit up, the onboard LED should lit up properly. So our hex file is loaded successfully, and then now program it. Programming complete. So let's see. As LED is lit up, so the program is correct, the reading and the writing is correct. the LED is on. Now what we will do next is to cross verify again. We will alter this value to AB. So we have written AA, but we are checking AB. So obviously the LED will now should be off. So let's see whether it is off or not. So let's again now compile this. Now the new hex file is loaded successfully. Again we program. Program complete. Now let's see. Okay, now the LED is off. So the reading and the writing operations are both correct, and the library EEPROM routines.h is working just fine as we have expected. So our reading and writing operations are both successful. Our program is successful, and this code will be uploaded in the GitHub link down in the description below. And so using this library in a future video, we will be using this EEPROM to store sensor data from a sensor like LM35 or from a solar cell. And but before that, we should be acquainted with using the onboard ADCs. So in a future video, we will be learning about using the onboard ADCs, and then we can move on to a more practical project in calculating the LM35 value or from a solar cell, and then storing that data inside the EEPROM. So that's all for a future video. So thank you for watching this video. So if you found this video useful, so please hit like, share and subscribe, and consider subscribing me and hitting the bell icon for getting further notifications. Thank you.